Hi there. Looks like you're only one here today. It's all right. You get your own personalized lecture on chapter 7. Well, I'm going to go ahead and just start talking. Record this. I had a couple join me and then they left. I don't know if they lost connection or whatever. But you have any questions?
No, I'm all good as of right now.
Okay, sounds good. All right, then, well, let me just continue where I ended up and we'll let others join. Okay, and if you feel that you got to go, hey, that's okay. I'm just gonna go ahead and lecture the rest of the chapters. And then
Yeah, I am the one who messaged you about having to leave a little bit early because of work.
Right.
So,
Yeah,
yeah.
no worries. If you have
All
to
right.
go, if you have to go, you got to go.
Perfect. Thank you so much.
No worries. All right. So what I'm going to do is, this is where we ended up. We ended up in this chapter. We're on chapter 7. We had just finished talking about all the different configurations that the shapes table has, and with some specific examples. And then I ended up in saying that hopefully, we should be able to, one, given any covalent compound or any polyatomic ion, to be able to draw the Lewis dot structure, okay? Because that aspect is important. We're going to learn in the next chapter about the polarity of the molecule, which is related to the bonds. But before we can do that, we have to understand the structure three-dimensionally, and that's what the electron dot structure gives us, okay? And then from the shapes table, we can determine what the shape it is and the bond angles. And then I left with this, saying to try this at home, pH 3, and then good old ozone, okay? Now, I can very quickly go over this one here. This one is just like ammonia. And if you go through it, you'll find that the Lewis dot structure will be as follows. Okay. And that will be the general formula of AB3E. Okay. Just like ammonia, the one we did before. Now, the ozone was a little more challenging. There's 3 oxygen atoms, and basically just treat one as a central atom, doesn't make a difference which one. And then the other 2 are bonded around the central oxygen. Now, we need to count all the valence electrons. So if we count, it's in group 6, there are 18 valence electrons for the 3 oxygens. Okay, so that corresponds to 9 pair. So now we can take one of the oxygens and just make it the central oxygen, and then pair up the other 2. And so that takes care of 7 pair. We got 2 pair. We got 7 pair to work with. So I just put them around all of them. Wherever you put them, just remember the octet. So we end up, I'm going to just go 1, 2, 3, 4, 5, 6, and then just add the last one in the center. So that is the 9 pair. That takes care of 9 pair. We still have 9 pair to work with. Keep track of your lone pairs here. And then check the octet. The octet for the left oxygen is good. The one for the right oxygen is good, but the center one is missing too. So as we did with the previous examples, we make double bonds. So doesn't make a difference which pair you take from. I can simply just take a pair from here, create a double bond. And so we end up with the following structure. And check the octet, make sure we still got 9 pair around us, which we do. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we didn't lose it. And then we figure out the general formula. We got A is central atom, B is 2, and then we put an E because we do have a lone pair on the central atom. Okay. So that's the general formula. Then you can take that and go to the shapes table and determine what the shape is. All right, so which brings us to bond polarity. So we've learned how to do dot structures for covalent compounds and for polyatomic ions, okay? And we're going to learn about bond polarity. Now, we have a covalent bond, which are the electrons are being shared when they're shared equally, okay? When they're shared equally, then we have what is called a nonpolar bond, okay? Nonpolar bond. And the best way to demonstrate that is using the generic symbols, the letter A, which is a nonmetal, and A, which is the same nonmetal. And that line represents the bond between A and A. Okay, so a good example of this would be all the diatomics like hydrogen, bromine, etc. The fact is that both A and A being the same, they have the same what is called electronegativity. Way back when we had talked about electronegativity. And electronegativity is a measure, it is the measure of the affinity of an atom that is bonded to another atom for electrons, the affinity to pull electrons onto itself, okay? Now, when they're both the same, like A and A, well, that pulling is equal. There's same amount of pull. And so we have what is called a nonpolar bond, okay? Another, and the key point here is A and A are the same atom, but there's an example that we're gonna tell you now is the carbon-hydrogen bond. Carbon-hydrogen bond, because the electronegativity is essentially the same, is also considered as a nonpolar bond. You might think, well, what is nonpolar? How do I relate that to the real world? Well, the best example I can think of is oil light. Okay, a lot of the oils like vegetable oil and motor oil and so forth are nonpolar bonds. And we know that oil and water do not mix because the next type of bond that we have would be a polar bond. So when we think about, one way to think about it, when we talk about a nonpolar bond, we're thinking about oil-like properties, okay? Which means that they won't dissolve in water very well, okay? So, and that's where polar bonds are. What's happening here is the two elements that are bonded are different. Okay, totally different. We have, in this case, I use the generic symbol of A and B, where they're different. The fact that they're different just tells you we have a polar bond. And a polar bond, think of it as like a magnet, if you will. We got a north side and the south side. It's the Earth is polar. A battery is polar. We got a positive side and a negative side, okay? Now, what that results in characteristics that make it more water-like, has more water-like properties, meaning that it would even be more readily dissolvable in water as compared to oil. Now, the difference what's happening here is that in the case of nonpolar bonds, where that electron is shared equally here, what's happening here, there is an unequal sharing, okay? There is an unequal sharing. And so one of these elements is pulling the electrons onto itself much more than the other. And which direction it's going depends on the electronegativity, okay? And to determine that, every element has an electronegative value. We don't have to memorize all of the electronegativity values, but we can remember that if we look at the periodic table, that fluorine is in the upper right corner, okay? And that, other than helium sitting here, but we don't worry about the noble gases because they have no polarity at all, okay? So in group 7, we got fluorine. Fluorine is the most electronegative element there is, okay? And so the trend goes from left to right, pointing toward fluorine. That's the trend. So from left to right, electronegativity goes up. In the bottom of the periodic table for fluorine, the electronegativity goes up. So if we were looking at a bond, and let's say, for example, we have a carbon-nitrogen bond, okay, notice there are two dissimilar atoms, automatically, we got a polar bond, no questions asked, we got a polar bond. The only exception is a carbon-hydrogen bond, all the time has a non-polar bond. Other than that, when you have two dissimilar atoms bonded together, you have a polar bond, okay? Now the question is, well, who's winning the tug of war? Well, then we go to the electronegativity of each one, carbon and nitrogen. We don't have to memorize it. We just look at the periodic table and we see that carbon probably is about right here and nitrogen's about right here, okay? And so that means that nitrogen is closer to fluorine than carbon is, which means that nitrogen has a higher electronegativity than carbon, and therefore nitrogen is pulling the electron density of that bond to the nitrogen. If I were to say draw a kind of a two-dimensional kind of cloud, kind of representing where the electron density is, the carbon nitrogen would look something like this, where the bulk of the density of electrons would be over here toward the nitrogen, okay? And I'm going to have an example here in a second when we go to the course website to learn more about a simulation that I have there. I have given for you guys to look at. Okay, so it's kind of skewed because electron density is being pulled toward the nitrogen. When we look at, say, carbon hydrogen, and if we were to draw a similar kind of, it would be uniform, not to scale here, but it'd be equally, the electron density would be equally distributed around the carbon and the hydrogen, all right? And so, and that, this polarity, bond polarity, plays a big role in the properties of the compound, okay? And so we have to understand it and really grasp this concept about bond polarity. Okay, so it's all related, as I mentioned, about the electronegativity, where fluorine is the most electronegative element. So we don't have to memorize the value for electronegativity of the elements. We just need to have a relative position to fluorine to tell us which direction, who is pulling the electrons toward itself, okay? And that's the trend, as I demonstrated. Fluorine's right here. Excuse me, fluorine. Fluorine's right here. That's our benchmark, okay? So that tells you that if you ever see a bond with fluorine bonded to it, then automatically the electron density is being pulled to the fluorine unless it's bonded to another fluorine. All right. So, for example, if it's fluorine bonded to fluorine, well, that would be a non-polar bond. Okay, because first of all, the fluorine, the same atom. Okay. However, if fluorine was bonded to anything else, let's say to nitrogen, then no questions asked. This is a polar bond. Furthermore, because fluorine is involved here, the electron density is pulled toward the fluorine automatically. So we create a pole, a dipole specifically, two poles, a positive end and a negative end, okay? And we're going to talk about that, about how to designate that. Okay, so all the covalent compounds are nonpolar bonds, okay? Including the carbon-hydrogen bond, okay? And it's considered to be a nonpolar bond. And if you think about it, a lot of the oils, like vegetable oils and so forth, a lot of them are just simply carbon-hydrogen bonds. And we know that they're very oil-like, and they won't dissolve in water, okay? I kind of use the distinction of oil and water. Oil-like, water-like. I'm not saying that it is oil, not saying that it is water. I'm just saying that because of the polarity, it would have properties of water and be able to dissolve in water if it's polar. And if it was nonpolar, it would have properties of oil-like properties and be more dissolvable in oil. And we know that oil and water don't mix. Case in point, Italian dressing. Italian dressing has two layers, right? You have the oil layer and the water layer. And anyway, it's a classic example. All right, most covalent bonds between two nonmetals, obviously. One of the atoms, when they're different, holds electrons tighter, and we call that, as I stated, a polar covalent bond. And so we have, to kind of summarize the two types of bonds, okay? So we have bonds here in the middle, okay? Now, if it is a combination of a metal, non-metal, okay, then we have an ionic bond, okay? That's an ionic bond. So a metal, non-metal combination. Over here, if we have a combination of a non-metal, NM, with a non-metal, okay, we have a covalent bond, okay? And underneath the covalent bond, we have two subsets. We have a polar bond and a NP nonpolar bond, nonpolar. And that depends on the electronegativity of the two species in that bond, okay? So some examples of polar covalent bonds would be like the carbon-oxygen, okay? Carbon-oxygen bond, you can see two different elements, a hydrogen chloride bond, sulfur fluoride bond, a silicon nitrogen bond, okay? Those are good examples of polar bonds, and you just simply put, there are two different elements, two different atoms, which makes it automatically a polar bond unless it's a carbon-hydrogen combination. Now, what we do, because of electronegativity, and as I stated, that one of the atoms is pulling the electrons onto itself, greater than the other, we use an arrow to demonstrate or designate in which direction it's going. We have an arrow here where we have the point will go to what is called the partial negative side. This delta symbol, this is lowercase delta, which means it's partial, not a full charge like ionic compounds where you have a full positive and a full negative. In covalent bonds, we have a partial, for polar bonds, we have a partial positive side and a partial negative because one of the elements is pushing the electron density tighter than the other, resulting in the one that has a higher electronegativity, it has more electron density around it compared to where the other one has less electron density around it because of that electrons that are being shared are being pulled toward one. And we designate which direction by the arrow. We have the arrow, the pointed arrow designates where the negative side, partial negative side would be. And then we have a positive end on the other side, okay? So if we look at a carbon fluoride bond, we know automatically that fluoride is the most electronegative element there is. So without question, that arrow will go from left to right, pointing toward the fluoride, because fluoride is the most electronegative, okay? Therefore, it would have a partial negative character, okay? And they're resulting in the carbon to have a partial positive character. This polarity is very important, especially in chemistry when we are making compounds and synthesizing compounds, and we depend on this polar bonds to place reactions on them, put reactions on them. If we look at our oxygen-hydrogen bond, the arrow in this scenario goes from right to left. Now, it could be written the other direction, but same thing, it's just the opposite direction. In this scenario, the arrow goes from left to right, with the partial on the oxygen and the partial positive on the hydrogen, okay? So, and then we got a phosphorus chloride. You know, you said, well, how do I know for sure which direction it's going? Well, again, take a look at their position. Okay, with the fluorides, no questions, automatically always go into the fluorides. Anything bonding to the chloride wins out. But the other is the oxygen and the hydrogen. Well, how do we know that arrow goes from right to left? Well, find the position on the periodic table. You'll see that hydrogen is in the far left and oxygen is much, much closer to fluorine, okay? Therefore, fluorine is a lot more electronegative. It has a higher electronegativity, which means that for that bond, the electron density is being pulled toward oxygen more so than hydrogen, okay? Resulting in a partial negative section, your area for the oxygen, and a partial positive for the hydrogen. Again, with the phosphorus chloride, find their position, arrive at the fluorine, and you will find that chloride, or in this case, chloride is right below the fluoride, okay? Phosphorus and chloride are in the same period, but the chloride is right below fluoride. So it's a lot more negative, electronegative than the phosphorus, and therefore the arrow goes from left to right. In general, when it comes to the halides, obviously the fluoride, but the chlorine, the chloride, the bromide, the iodide, they always win. They always win as far as the electronegativity. Okay. They tend to have higher electronegativity. Now, obviously, noble gases don't have electronegativity because their octet is full. They don't have a need for any more electrons. They got that magical 8 number, so they're good to go. Okay. All right. So here they might ask you, well, write the delta notation, which is the delta partial positive and partial negative, and then the polarity arrow, where the arrow point goes to the most electronegative element. So again, here we have carbon and oxygen. Find its position on the periodic table, and oxygen is a lot more electronegative than carbon because oxygen is closer. And so we can draw the arrow from left to right, okay? Which means that partial negative on the oxygen, partial positive on the carbon. We have a nitrogen oxygen, no questions asked here. You don't even have to look it up because fluoride is the most electronegative. So the arrow goes from left to right. Partial negative on the fluoride, partial positive on the nitrogen. Here we did the oxygen already, hydrogen bond, and it's going in this case from right to left. Partial negative on the oxygen, partial positive on the hydrogen. Carbon to chloride, the chloride is always a lot more electronegative than the carbon, so it's going from right to left, resulting in a partial negative on the chloride, partial positive on that. None on the carbon-hydrogen bond. Why? Because it is a nonpolar bond, okay? So there's not a dipole, okay? Remember the term dipole means we got two, either positive negative side or a north and south side, so to speak, okay? Two poles. All right, let's clear this up. And here we go. All right. Now, the question here that is asked is, are the bonds ionic? No. For ionic, as that flow chart I drew earlier, to be ionic, it has to be a metal-non-metal combination, okay? And the only one here with that combination is sodium and chloride. Okay, so that is the only one that is ionic. All the other ones are covalent. Okay, and so the question after that is, okay, who's polar, who's nonpolar? Well, the fact that we just stated that this is covalent, and that furthermore, the fact that there's two dissimilar atoms bonded automatically tells you that these are polar. Okay, this one's ionic because of the metal-nonmetal combination. The others are covalent, but to describe it further, we have to just simply see that there's two different. And so this is the AB scenario. This is the AB scenario. And this one here, the bromine-bromine, is simply the AA scenario. So this will be nonpolar. Okay, so you see how we did that? And you're going to get a lot of examples like this, either in homework or assignments where you're given a particular bond and you're asked to determine whether it is ionic, and if it's covalent, is it polar or nonpolar? Okay. Nonpolar for the bromine, polar for the phosphorus fluoride, and we're talking about the bond itself, not the whole molecule, because we're going to take this information once we identify once we learn how we identify whether a bond's polar or nonpolar, then we're going to take that information and put it together with the Lewis dot structure, and that would then help us to determine whether the whole molecule is polar or nonpolar. Okay, so that's how we try to bring it in. So polarity is it's going to be showing up all the time, over and over again. And just think of it as a tug of war of bonded electrons. Okay, and the one element that has the greater bonded electrons is going to win the tug of war, and it's going to pull the electron density more onto itself. Okay, so what I want to do is, let me share, we'll come back to this. Let me share this here. Now, on the course website, in one of the modules, there's a module called Additional Chemistry Resources. Okay. Now, if you click the molecule polarity, okay, I don't know what's going on, but it's been try this again. The canvas has been acting up quite a bit. Something's going on here. Let's try this again. All right, here we go. And then there's a link, and you click on that link, and it sends you to the simulation website. And just select 2 atoms, okay? And I will go up here and click the partial character. You can put bond character and electrostatic potential or electron density. I kind of like the color difference. And now all is it's saying here, and then down here, there's 2 atoms, A and B, okay? Now, right now, this AB, because the electronegativity of A is, they're both the same, there's an equal sharing of that bond of those electrons right in the middle. And you can see around it, it's just a uniform color. Now, when one atom increases in electronegativity, it's going to start to draw the electrons onto itself. In this area, I'm going to shift over the B and increase its electron density. And notice that the color on the right side becomes red, okay? Red in color and darker in color, where on the left side, it becomes blue. Also notice that because of the electronegativity, you're going to start seeing the partial. Notice the partial designation is pretty small right now, but as we increase the electronegativity, you can see it increase. So we got a partial negative on the right, partial positive on the left, and then the dipole arrow shows up. And right now it's pointing toward B because we told it that it has a higher electronegativity. Okay, so that's, I like the color difference between the blue and the red. You can see it, but you know, you can also demonstrate that with grayscale, where the darker the color, the more electron density going to B. Okay. Now, also, this is movable because we do have a partial negative. It's a dipole bond. It will be affected by an external electric field. So we put a plate here with a potential positive and negative, see, and we move it around, notice how the molecule lines up. So the partial positive is attracted to the plus plate, and the partial negative is, excuse me, the other way around. The partial negative is attracted to the positive side of the plate, and vice versa for the other end. Okay, and so that is what happens. Now, when you have a scenario like this, that is a permanent dipole. Permanent in that you're always going to have a dipole because the nature of the beast being the two different elements, one having a higher electronegativity than the other. So that's a permanent dipole. Okay. And when the dipole, when the elements are, you know, the electronegativity are the same, and then you have a nonpolar bond. This is an example of a polar bond. This is an example of, excuse me, example of a nonpolar bond, example of a polar bond. Okay, so the difference here. So yeah, we have this, you have this there, you can do all kinds of different things and play with it. It'll show you the difference of 3 atoms and its electronegativity and so forth. It affects the overall. It will affect the overall dipole or polarity of the molecule. Okay. So, all right, let's go back. All right, so in here, they're asking you to determine, looking at the bond, and determine who's ionic, just like we did before, who's polar, who's nonpolar. Okay. And so by definition, ionic, which is the easiest one to do, is a metal, non-metal. So we can go here and isolate all the metals and non-metals. So sodium chloride, definitely ionic. HCl, no, they're both, that's covalent. HH, covalent. Cl, chlorine, carbon, covalent. Carbon, hydrogen, covalent. Oxygen, oxygen, covalent. Potassium and oxygen, definitely ionic. And then phosphorus and fluoride, covalent. Okay, so we only have 2 examples of ionic compounds, which means all the other ones are covalent. All right, now, so we're going to go back and check it out. We got a covalent. So this scenario, okay, we got an HCl. That scenario is an AB scenario. Okay, 2 different elements. Automatically polar, covalent. Okay. I think I'm just going to shorthand it right now and just say PC, polar, covalent. H and H. Well, that example is an AA scenario. Okay. And so that would be non-polar covalent, and PC. Okay. We have the chloride carbon, definitely an AB scenario. And so that would say polar covalent. Carbon hydrogen, remember that is the only example of a AA scenario because the electronegativity of them are of the carbon hydrogen essentially the same. So we have a non-polar covalent species. And then oxygen, that scenario is an AA scenario with respect to what's bonded together. So we have another non-polar covalent. We know about potassium. And then the last one, definitely an AB scenario. We have phosphorus and fluoride. So we have a polar covalent compound right here. Okay. Now, for the polar covalent compounds, we're going to draw the arrows. All right. So now we go and we're looking at this one, and this one. Okay. A hydrogen chloride. Well, the chloride is a lot more electronegative, than the chloride than the hydrogen. So the arrow goes from left to right, meaning there's a partial negative on the chloride, partial positive on the hydrogen. Okay. Carbon chloride, similar scenario. Chloride's a lot more electronegative. So in this scenario, the arrow goes from right to left, giving us a partial positive on the carbon and a partial negative on the chloride. Then we got the last one, the fluoride, no questions asked. The fluoride wins the tug of war. And so we have an arrow going from left to right, okay? Partial negative on the fluoride, partial positive on the phosphorus. All right. Ionic, so on and so forth. And then the arrows that we just talked about. We didn't do the arrows here, but if you need it, you should be able to do it. Okay, which brings us to the molecule. Okay, so the bonds themselves tells, if we know they're polar or nonpolar, will give us information as to the whole molecule. Okay, now, when you have a molecule that contains nothing but nonpolar bonds, that means that the nonpolar bonds results is equal to a nonpolar molecule. And so all the hydrocarbons, let's say, for example, I know you're not familiar with this, but I'm going to show you anyway. Oh, here's some. Okay, CH3. Okay. This is the formula for ethane, okay? Or even better than that, something that we're all familiar with, propane. CH3, CH2, CH3. Okay, this is the formula for propane. We're all familiar with propane. Right? Propane is a gas, and also we use it to do our cookouts, cooking with propane tank. Well, if you look at that structure, you have nothing but carbon-hydrogen bonds and carbon-carbon bonds, which is two equal elements. So everything in there is an A scenario, which is the results in that propane is a nonpolar molecule, okay? All hydrocarbons, these are the generic name for this, all hydrocarbons are nonpolar. Now, when we get to polar bonds, okay, let me explain these two here. We had done the geometry for both of these. This is sulfur dioxide, and this is carbon dioxide, okay? Now, with sulfur dioxide, we ended up with a lone pair in the central atom. And because of that, that causes that bond angle to be less than 120, okay? Because that lone pair in the central atom spreads out and needs more space, and so it causes that bond angle to shift. What that results is this: if this were a molecule that had symmetry like this, any molecule that has symmetrical, and that they have polar bonds, those polar bonds will cancel each other out. What do I mean by canceling out? Well, these arrows are what are called in mathematics vectors. That's not important. What it means is they have magnitude and they have direction. So if I said to you 50 miles, that means nothing unless I say 50 miles east. I go 50 miles, it gives me magnitude 50 miles plus I have direction east, okay? The result is that graphically, I can add and subtract these arrows. So if I have an arrow like that, going from left to right, is going in the positive direction, okay, from our axis. Remember, our axis is here's a 0 point, right? Anything going in this direction is positive. This direction is positive. Over here is negative direction. Down is negative direction, okay? And so this arrow is going in the positive direction, and it has a certain distance, and we can assign an arbitrary value and just say 5 units, okay? Now, if there's another arrow going in the same direction, also the same width of that arrow, same magnitude, in the same direction, totally, they have 10 units. I can just simply sum up this units. They're going, their total contribution is the sum of each one, okay? Now, if I turn one of these around and have it go in the opposite direction, and so now it's 5 units in the negative direction and 5 units in the positive direction, the result is the net is 0. So these arrows, depending on the direction, can cancel each other out. And so if we looked at carbon dioxide, if you recall, this is the formula for carbon dioxide. It was an AB2 general formula, and that was linear. We got one arrow going to the right in the positive direction, and then one arrow going to the left in the negative direction. That represents the dipole of the carbon-hydrogen bond. What results is just like this scenario, this carbon dioxide is nonpolar because the polar bonds cancel each other out, okay? And if this was this trigonal planar configuration, and these were polar bonds in this scenario right here, they too will cancel. Another one would be the tetrahedral, where you have A, B, and B, tetrahedral, because of the symmetry. If these were A, B were polar bonds, and all of these would cancel out if all the B's the same. So this would be a nonpolar bond. This would be a nonpolar bond because the polar bonds cancel each other out. When they don't cancel each other out, then you end up with a polar bond. And that's the example of sulfur dioxide. When you do that, you can see that the arrow to the right is going to the southeast direction, okay? And the arrow to the left is going to the southwest direction, all right? So they don't cancel each other out. So the sum of those two is somewhere in the center, okay? But the result is this: since they don't cancel each other out, then SO2 is a polar molecule with polar bonds, okay? So it is possible, here's the important part, it is possible to have polar bonds like carbon dioxide and end up being nonpolar because the polar bonds cancel out, okay? So, and that's why the Lewis dot structure is important, because we need that information to determine, because on the surface, you would think SO2, CO2, they look like they would have the same structure, just simply because of the same number of atoms, and that's not the case, okay? Because the Lewis dot structure tells us this is the geometry of SO2, and this is the geometry for carbon dioxide. And then we can look at the polar bonds and see if why one is polar and why the other one is nonpolar. Okay, so geometry plays a crucial role. Now we talked about. I used an example earlier of propane, and there was nothing but carbon-hydrogen bond. Here, CH4, this is methane. And we have that's just carbon, hydrogen, and definitely nonpolar molecule, okay? PCl3, analogous to, if we were to do, and I'll leave that up to you guys, is if you do the Lewis dot structure, you end up with a structure like this, which is AB3E, okay? Now, anytime you end up with lone pairs on the central atom as a general guideline, you have a polar molecule, okay? Some molecules can have two pairs of lone pairs on the central atom, definitely very polar. Water is like that. Water has two lone pairs on the central atom. Water is extremely polar. So this example of trichlorophosphate trichloride having a lone pair on the central atom tells you automatically, I have a polar molecule. And again, because this lone pair take up a lot of space, you would think this would be like a tetrahedral configuration, but it's not. Okay, because of this lone pair, they squish that bond angle, resulting of it coming out not being a tetrahedral where they can cancel those polar bonds. The polar bonds will cancel out because of geometry, but the lone pair pushes it out of the tetrahedral configuration, resulting in a polar molecule. Okay, so this is polar, and then we just talked about carbon dioxide, where that is the Lewis structure, and in this scenario, the polar bonds are opposite of each other, and being opposite of each other, they cancel each other. Okay. Yeah, we talked about these here. I just talked about water. Very polar. In fact, water is the most polar solvent that we have. And then we had ammonia, which is like similar to, we did this before, we got a lone pair on there. And so lone pair automatically polar molecule. All right, well, tell you what, we are done with chapter 8. All right. Bear with me for 1 second. I need to do something real quick, and then we will start on chapter 8, which deals with nomenclature. Okay, so bear with me. Okay, I'm back. Okay, don't forget, today is the for the lab. It's a midterm exam for labs 1 through 5, so don't forget about that. All right, chapter 8. Chapter 8 deals with nomenclature. Okay, nomenclature is nothing more than naming that compound. So what we're going to do in this chapter, obviously, we're going to learn about the names of the compound, but we're also going to learn how to put them together to make molecules. Okay, and there's two ways of naming these compounds. One is the ionic method for ionic compounds, and then the method for covalent compounds. And the only difference between the two really is that for ionic compounds, we don't use prefix like di, tri, etc. Covalent compounds we do. Okay, hence you have carbon dioxide, carbon monoxide. Okay, and we don't switch it to ionic compounds, no prefixes. Covalent compounds, prefixes. All right, so simple neutral atoms, we just, obviously we talked about this, it's sodium atom, and we always use give the name of the element and then throw in there the word atom. Okay, so be familiar with the first 20, which we have talked about, and then we're going to add some more. We got barium here. CO is cobalt, I is iodine, Cu is copper, Fe is iron, Pb is lead, Hg is mercury. Ag and Au get confused a bit. Ag is silver, Au is gold. Then we got Zn for zinc, and Sn is stannous. Okay, you can use that word, or preferably the word that's used most often is tin, Tin. In fact, a lot of the toothpaste, check your label on your toothpaste, you probably have a stannous fluoride. And some of you may have sodium fluoride, but some toothpaste uses a tin fluoride. Then we have strontium, nickel, bromine, chrome. This one gets confused with Mg. This is manganese, not to be confused with Mg, which is magnesium, okay? And then we have K. And we'll probably add a few more as we go along, but those are the ones we're going to start off with. But some of those are the same as the list we had given earlier. All right, so ionic compounds, this is a rehash. You know, how do we define what an ionic compound is? And that is a combination of a metal and non-metal, okay? And whereas covalent compounds are defined as compounds that are made up of non-metals only, aka molecular compounds. We have monatomic atom ions. We talked at length about that too. We have the positive ions and negative ions. Positives are also called cations, and the negatives are called anions. Now, the driving force for ionic compounds is that metals lose electrons and non-metals gain electrons to obtain that magical 8, to obtain the 8 electrons around its valence shell. Okay, that's the driving force for them to do that. Now, the other big difference between an ionic compound and a covalent compound is the type of bonding. We just talked about that. Okay, if we look at, let's say, sodium and chloride, we got sodium here with a positive and the chloride here with a negative, they just attract each other. We have this electrostatic attraction like two magnets, okay, combining here. They're not touching, they're touching, but they're not sharing anything. They're not sharing the electrons. Unlike what a hydrogen chloride bond, where we are actually, and that circle kind of represents the electron density, we're sharing that pair of electrons there, okay? But we're having unequal sharing because it's a covalent compound. In this case, we have partial negative on the chloride, partial positive on the hydrogen, and there's a sharing going on, okay? That's for a polar covalent bond. And for a nonpolar, like hydrogen, we have an equal sharing, equal distribution of electrons density of that. So this would be a nonpolar. The other difference is this, is ionic compounds, when we put them in water, they will dissociate and break apart. Covalent compounds don't do that, with one exception, and those are acids. And we'll talk about that when we get to that chapter. But that's a big difference. So if you get pure water, which won't conduct electricity because there's no ions, and you put in an ionic compound in there, the ionic compound will dissociate. Sometimes a full 100% dissociation, or sometimes maybe much smaller, but nevertheless, regardless of the magnitude, there are some ions that go in solution, which then results in a conducting solution. It will conduct electricity. Whereas covalent compounds, you put them into pure water, those that are soluble in water, there's no conducting of electricity because there's no ions being formed, okay? All right, now we have polyatomic ions. Now those, we're gonna be using those quite a bit also here. And I direct you to the periodic table. And if you look at the periodic table, down here on the bottom left corner, we have the polyatomic ions that we'll be utilizing. Now, the takeaway from these is this. These are polyatomic ions. These are covalent compounds, have a negative charge on them. They are ionic. They are ions. Okay. And they're ions for the reason we're going to learn how they become ions. And most of these start off as acids and react with bases, which we're going to learn about, I believe, in the next chapter, to form these ions. But they're covalent compounds with a charge, and they are called polyatomic ions. They have a specific name. Okay. So this one, NO3 negative, has a specific name, nitrate. It is not anything else. It is nitrate. We don't call that nitrogen trioxide. That would be incorrect because it's not truly ionic. There is a difference between this one and this one. Okay. The top is an ion. This is nitrite ion because it is a polyatomic ion. Okay. And this is nitrogen dioxide. This is covalent, okay, and not an ion. Okay, not an ion. So both of them are covalently bonded, but the top one became an ion to have a negative charge on it. Okay. And it has its specific name, nitrite. Let's do that. Go back here. So we keep the name, we don't change it, you know. And if we need to demonstrate more than one ion, and it's possible that we can, because we need to demonstrate we need 3 or 4 maybe, we put a parenthesis around the formula, around the NO3, and then we subscript it with a number greater than 1 to demonstrate we need whatever number that we need, okay? All right. So up to this point, I've been using the name charge. You know, I talked about ions have a positive charge or a negative charge. And now we just introduced nonpolar bonds, the polar bonds that have a partial charge, okay? They don't have a full negative. They don't have a full positive. They have a partial, okay? So we really can't talk about partial. So what we do is use the term oxidation state, which is essentially the same, be it a partial charge or a negative charge, but using the term oxidation state encompasses both ionic and covalent compounds to describe what their respective oxidation state or what charge, if you will, charge they would have, okay? So I'm going to be using the term oxidation state because we're going to be talking about the oxidation state not only in ionic compounds, but the oxidation state of covalent compounds. Okay. Now we understand now, hopefully, that all elements have a 0 charge. Why? Because they have an equal number of positives and an equal number of negatives with respect to their charge. And when elements get a charge, when they become positive or negative, it is because they have either lost or gained electrons. Okay. Now, let me go to the periodic table. I have on my periodic table the following information listed out, and my suggestion is maybe also to have it. Oh, we got one more person coming. And my suggestion is to do the same because this information we're going to need to know. Okay. And I circled the first group. Everybody in group 1A will have let me change the color here. Everybody in group 1A, lithium, sodium on down, all of them have in common, as we know right now, hopefully, that they have one valence electron. They are all metals, and they will all lose electrons, and therefore everybody in group 1A, everybody, all 6 of them, these elements, would end up with a positive 1 charge because they lost 1 electron. Everybody in group 2A, okay, 100% of the time, they're metals, they will lose electrons, they specifically will lose 2 electrons because you got 2 valence electrons here. Okay, it is much easier for these metals to lose these 1 or 2 electrons because first of all, point 1, these metals relative to the nonmetals, radius size, they're bigger, okay? Meaning that those electrons are further away, okay? And don't interact with the nucleus as much. So that's point 1. Point 2, they're striving for that magical 8. And so everybody in group 1, from an energy perspective, the likelihood of gaining 7 electrons is just, from energy perspective, probability extremely low. Never say 100%, yes, it can happen. No, it can happen. There's always exceptions to the rule, but it's probability very, very low to gain 7 electrons for the group 1 or to gain 6 electrons for group 2. Energy, Mother Nature wants to take the easy route, and it's easier just to get rid of those 1, 2. Okay, so those 12 elements have 100% time, their exact charge. Okay, and that's important because when we start naming these compounds, we're going to not deal with Roman numerals, and I'll explain that in a minute. Okay, on top of that, there's 4 more. Aluminum always has a +3, 100% of the time. Zinc, which I circled, always has a +2. And then silver, Ag, not gold, but silver, Ag, always has a +1. And then its neighbor to the right, cadmium. So I kind of look at it as like a little diagonally back 1. That helps you out. Okay, always has a +2. So there are 16 elements, which I call the sweet 16, okay, that 100% of the time their oxidation state, okay? That means that everybody else, all the other metals here, everybody else have what is called a variable oxidation state. For example, copper can have either a +2 oxidation state or a +1 oxidation state. And the way we distinguish between those two is we use Roman numerals, capital Roman numerals. Okay, we're going to have some examples here in a second. Okay, we don't use Roman numerals for the sweet 16. They're simply whatever it is. So it's sodium chloride. Sodium is part of the sweet 16 here. So in the name of that compound, just sodium, we wouldn't say sodium Roman numeral 1 chloride. That would be incorrect, okay, with respect to naming that compound. Now, on the other end of the spectrum, for the nonmetals, for group 5, and I'm circling the ones that we're going to use the majority of the time, group 5, nitrogen and phosphorus, all the time, 100%. They're nonmetals. They got 5 valence electrons. Pick up 3 is not a problem as compared to getting rid of 5. Energy perspective, getting rid of 5, a lot more energy required than to just dump in 3. You dump in 3, why? Because they got room for 3, okay? There's room for 3 electrons in the group 5 elements. Having room for 3, they're going to end up with a -3 charge, okay? Group 6, which again, I'm just going to circle the ones that we use quite a bit, and that's oxygen and sulfur. They are group 6. They're 2 electrons away from fulfilling the magical 8 number. And so again, in this scenario, they're going to pick up 2 electrons, resulting in a -2 charge, okay? And then finally, and again, I'm circling the ones that we use most of the time. Does not mean the ones that don't circle, that doesn't happen. We're circling what we do use quite often. These are the halides. The halides, all of them, every single one of them in that column, have 7 valence electrons. They differ in the total number of electrons, but they all have the similar property of having 7 valence electrons, which is 1 away from that magical 8, okay? And therefore will, being a nonmetal, will gain 1 electron, resulting in a negative charge, okay? So those are the negative the negative charge species that you know 100% of the time what their charge would be. Furthermore, with respect to the ones in red, their name remains the same. So sodium is still sodium if it's either as an elemental form as an atom or as an ion. And the only way we can distinguish the two is to write the word sodium atom or sodium ion. The nonmetals, that's not the case. The nonmetals, the name goes from whatever the name is, and we add the suffix IDE. So nitrogen becomes nitride, okay? Nitrogen becomes nitride. See that, okay? Phosphorus becomes phosphide, okay? Oxygen becomes oxide. Sulfur becomes sulfide. And then you can do the rest of them. There's fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide. So we're changing the ending to have the IDE. The IDE should tell you that you're dealing with the anion of the nonmetal, and furthermore, you're dealing with just the atom itself, not multiple atoms around there. Because if you look at, let's take, for example, the nitrate, okay? There are N, which is nitrogen. Okay, let me do it this way. It's getting a little messy here. Let me do it this way. And we're gonna work with nitrogen. So we got nitrogen, okay, with the symbol nitrogen and the element name. Okay, it is in group 5A, so it will gain 3 electrons. So now it picked up 3 electrons. So now we change the name to nitride. Now there are times that nitrogen will be bonded to oxygen. Okay, specifically, you go to the polyatomic ions, you will find nitrogen bonded to 3 oxygens, and it's a polyatomic ion. Okay, and it has a negative charge on it. This species is called nitrate. Okay, now, if you have nitrogen bonded with 1 less oxygen, we're going to talk about this naming of oxy polyatomic ions, and when we're done with this chapter. This is called nitrite. Okay, we got the IDE, the ATE, and the ITE ending. Okay, the IDE is simply the atom itself with its respective charge. It could be nitride, it could be oxide, it could be fluoride. Okay, then when we throw in the 8, when you read that or read 8, that is nitrogen, because you got the Ni telling you it's nitrogen, then the 8 tells you, oh, I got oxygens bonded to that nitrogen, specifically 3 of them. Okay, and they differ because you got sulfur, for example. This is called the sulfate. And we have S for sulfur. Okay, S-2 for sulfide. Okay, and then the sulfite is SO3 -2. Okay, note the difference. Here we go again, 8 and 8. Within the sulfur, there's a difference between 4 and 3 oxygens. Within the Ni nitrogen is a difference between 3 and 2 oxygens. Okay, so 3 types of nitrogen, 2 of them bonded with oxygen, and there's more of these types that we're going to have a whole talk about when we're in with this nomenclature, where we have hypo, nitrite, and so forth. When we talk about that and how to determine what they are. Okay, so that is the difference here that you have to be aware, because those names could be given to you in a word, a sentence where you're asked to, you're given an equation and you're asked to write that equation, given us a sentence with the reactions in words, and then being asked to change those words into formulas and to write an equation out. Okay. All right, so these are the fixed oxidation numbers that you should be aware of. We talked at length about metals losing electrons, become cations. We know group 1, group 2A, group 3A always have a +1, +2, +3 respectively. Then we added the other zinc, cadmium, and silver with their respective charges. That's part of the sweet 16. We got to know that. That means that all the other metals, depending on their reaction conditions, their oxidation state could vary from a +1 to a +9. Okay. And we have to distinguish those with Roman numerals to tell you what oxidation state you're working with that particular metal. For example, we got here copper 2. Okay, we have copper 0, which is the element of copper, right? It has a 0 charge because equal number of protons and electrons. Copper can lose 1 electron, and we end up with copper +1, okay? Or it can lose 2 electrons, and we end up with copper +2. All right, so essentially have 2 types of copper. Now, copper 1 and copper 2, totally different species. Copper 1, copper 2, one of them has a very nice blue, beautiful blue color, and a lot of dyes and stuff have that material in it. And then a lot of them have, excuse me, then the other one has like a greenish color to it. Okay. I was going to say, growing up in my hometown of Superior, Arizona, which is a mining town, copper mining town, I used to play in a lagoon that had a blue color solution. And we as kids thought that was cool, you know, got blue color. We thought we had the ocean out here in the middle of the desert. Well, I didn't know exactly what I was dealing with until I became a chemist, and that turned out to be a copper cyanide compound. That was cyanide was one way to use to extract copper out. So all this copper is in solution. We were playing with it. Surprised I'm not growing something out of my side of my head or something. Knock on wood. Anyway, a lot of heavy metals up there. So to distinguish those different types of coppers, we use Roman numerals. So for copper, when you see copper +1, it will be copper. You will draw this different color. It will be, you will write this out, copper, Roman numeral 1, parentheses. And then this one will be copper, Roman numeral 2, parentheses. Don't forget the parentheses. So down here, we got copper 2 is the +2 oxidation number. Iron will be written as iron 3. Lead will be written as lead, Roman numeral 4. Okay. And like I stated, those metals, all the metals can vary from a +1 to a +4. All right. Now, most of the time, you're going to be given this information, but you can also calculate which oxidation state your metal is using. Okay. And I'll show you that when we start putting these ions together to make compounds. I'll show you how you can do that. Okay, so we talked at anions about it, excuse me, about anions. Gain electrons. Group 5 always -3. Group 6 -2, etc. Group 7 -1. Okay, obviously the noble gases, nothing's going to happen to them. Okay, they're together. They're happy with their 8, and helium with its 2. Excuse me. So we're going to learn about naming or putting together ionic compounds. Okay. Now, the names I just explained, like the nitride, the oxide, the halides, and so forth, that naming is not just for the ionic compounds. We're going to keep that naming nomenclature to covalent compounds, like carbon dioxide. Okay, for example, let me think of here. Oh yeah, okay, so we know that this is carbon dioxide. Okay, we're all familiar with this. And then this one is ionic, and this is called sodium oxide. And so the name for oxygen being either bonded covalently or bonded ionically, we still maintain oxide, the same name, okay, for both of the types of compounds. And it's true for the fluoride, the halogens, and all of the other ones. All right, so the sum, when we start putting these together, they're made up of ions. So the total number of cations plus the total number of anions that we put together must equal 0. Okay, and so number of cations plus the number of anions equal 0. Okay, and that's like 99% of the time. Okay, when you end up with a neutral compound, but it is feasible to have a non-neutral compound. For example, the polyatomic ions have a charge, all right? And so we could really make a more broader equation to say the total number of positive oxidation numbers plus the total number of negative oxidation numbers would equal the charge of the compound. And that, I think, encompasses more things than just cations and anions, because the total number of positive oxidation numbers, be it covalent, be it ionic, plus the total number of negative oxidation numbers, be it covalent, be it ionic, would equal the total charge of the molecule. And 99% of the time, the total charge is 0, okay? But the top equation kind of encompasses more, so that allows you to calculate the oxidation numbers of other species, and we'll do some examples of that. But first, let's learn straightforward, everything equals to 0, okay? Now, the polyatomic ions, I talked about this, here it is again. These are units. Now, if, for example, you need to use more than one of these, like you need maybe 2 units of nitrates, right? We would utilize a parentheses like so with a subscript, and say we need two nitrates for whatever reason, or 2 nitrites or 2 sulfates or 3, whatever. If you only need 1, you don't need a parenthesis, no parentheses put in. But more than 1, you put a parentheses, and then you subscript what, how many you need, okay? And like I said, their name, that is their name. That's nitrate. Here's acetate, here's a cyanide, so on and so forth. We don't change the name. So this is not, NO3 is not nitrogen trioxide. Okay, it is called nitrate. Okay, and if you need more than 1 nitrate, it is still called nitrate. So we wouldn't call it dinitrate. This would not be dinitrate nor trinitrate, just be nitrate. No prefixes when it comes to ionic compounds. Okay. Compounds, let me fix this a little bit here. Hold on a second. Okay, formulas for ionic compounds. Compounds must be neutral. So we're going to add enough cations, enough anions to equal 0. All right, so You may be given this is make a compound, make a formula for these two elements. Well, step number one, okay? Step number one, this one and this one, is you take the element and you convert it to the ion form first before you start putting anything together. We know that sodium is a group 1, so it will have in ionic form a +1 charge. We know that nitrogen is a nonmetal, group 3, group 5 will gain 3 electrons, so it would have a -3 charge. Okay, so step 1, we put them in ionic form. Now we determine how many of each we need, so that when we put them together, they equal 0. So we need 3 sodium plus to cancel out the -3 of the nitrite. So this 3 that I put in front of sodium ion becomes the subscript for sodium. So when I write the formula out, it would be Na subscript 3N, and that would be the name sodium nitrite, not sodium nitrogen, because it definitely is not the element nitrogen. It is the ion of nitrogen, which is nitrite. Okay. Now also make sure it's subscript, because this sodium with a big coefficient, that would be incorrect. I have no idea what that is. Okay. But the subscripts tell you how many of those atoms you have. Okay. All right. Excuse me 1 second. All right. So somebody's knocking at my door. They can wait. So that is the formula. Na subscript 3 nitrogen. The name sodium nitrite. We don't change the name of the metal. It remains the same. All right, so we have another, okay. Step number 1, they're asking you to write the formula of sodium and the sulfur atom. So first step, convert those into ionic form. So as we did with sodium, it's a +1. Sulfur, you have to determine what group it's in. It's in group 6. So in ionic form, it would have a -2, right? Because it's going to pick up 2 electrons. Furthermore, its name now went from sulfur to sulfide. All right, so here we need 2 sodiums for every sulfide. So its formula is Na subscript 2 S. Name, we'll get the name in a second. I'll write it down, but the sulfur, sodium sulfide. Okay. Okay, next one, magnesium and oxygen. Ionic form, magnesium's in group 2, so it has a +2 charge. Oxygen, like sulfur, same group, so oxygen has a -2 charge. Furthermore, its name now becomes oxide. Okay, we got magnesium +2, oxygen -2. Straightforward 1-to-1 relationship. We can just put them together because they have enough charges in each one to cancel each other out. So that is the formula for magnesium oxide. Okay. Next one. Same scenario. Potassium is in group 1, like sodium, so it will have a +1 charge. Phosphorus is in group 5, so as an ion, it has a -3 charge, phosphide. Okay, which means that we're going to need 3 potassium ions to cancel out the 3 charge oxidation number for the phosphide. So its formula becomes K subscript 3E. Okay. Next one, a little bit of a challenge. Let's clear this up a little bit. Some room here. We got calcium and nitrogen. Well, calcium is in group 2. So we got a +2. Nitrogen, again, group 5. So ends up with a -3 charge. Okay. So here you're looking at this, you see you got a +2 and a -3. Unlike the others where you can increase the number of one of the cation or the anion to put them together, here I can't, Because if I put them together as simply a 1-to-1, well, that species ends up with a -1 charge left over, right? Because I got a +2, cancels out a -2, leaving me behind a -1. So that would be incorrect. That would be the correct one, yeah? And so, what options do I have here? Well, what do we do when we say add a fraction, 1/2 plus 1/3? Okay, what do we normally do? Right? Don't we look for a LCD, lowest common denominator, or a common number? Okay, for these here, the common number would be 6, right? So I convert the 1/2 to 6 and the 1/3 to 6, and I'm good to go. I can add it up now. Well, we got a similar scenario here. The common factor between the calcium ion and the nitrite is also 6, right? So what I need to do is I need 3 of the positive calcium to give me a total of +6, right? And I need 2 of the negative nitrites to give me a total of -6. So -6 plus a +6 gives me a net 0. Therefore, I need this. The numbers I just wrote here become the subscripts for those compounds. So the formula becomes CH subscript 3 and the nitride subscript 2. It's still called calcium nitride. Now, there's a little, I don't want to call it trick, but if you observe something, it's a tool you can utilize to help you out to look at a glance how to write the formula. Let me change the color here. If you look at the subscript of the anion, which is a 2, isn't that the oxidation number of the cation, right? And if you look at the subscript of the cation, that is the oxidation number of the anion. Okay, so you can use that to help you write the equation fairly quick. But if you don't see it, not to worry, go through the scenario we just talked about, look for a common number between the two, and then just multiply each one with a factor to get you to that common number, okay? And then that factor becomes a subscript for that particular atom, or ion, I should say. All right, aluminum and chloride. Aluminum always has a +3, and the chlorides always have a -1. They're in group 7. So that means I need 3 of my chloride, 3 chlorides for every aluminum +3. Okay, so its formula is AlCl2. And then we got zinc, which always has a +2. It's one of the sweet 16. Zinc always has a +2. Iodine, like the chloride, is in the same group, has a -1 charge as an ion. I just need 2 of them to cancel out the +2 of the zinc. So its formula becomes ZnI subscript 2. Okay, now recall everything up to this point has been exact oxidation numbers. Now we get the copper, which is not part of 16. So we got to tell you what oxidation number you're working with. That Roman numeral tells you that you're working with copper 2 +2. The oxygen is a -2. Okay, just like we calculated up here from number 2. So I can put them together as straightforward as a 1-to-1. All right. All right, so that's the formula for copper oxide. All right, let's do one more. So here we have lead, Roman numeral 4. So we're working with lead plus, phosphorus, lead +4. And then the oxygen, as we just stated earlier, is -2. So I need 2 oxides for every lead +4 ion. And so the formula becomes PbO2. Okay, now let's just quickly do some names on this thing. Now, the other aspect is this: you can mix and match. Okay, take your sodium and combine it with the oxide, combine it with the phosphide, combine it with the nitride, combine it with the chloride and the iodide. The same with magnesium with the sulfide and the phosphide, etc. You can do a mix and match. You can start building up your database. You're already probably up to a couple hundred compounds that you can put together. And that's not including all the other metals that we haven't even talked about here that you can utilize to do a mix and match. So you can see you already can create a large number of compounds to work with. So the first one we did was sodium sulfide. Sulfur becomes sulfide. Now, the sulfur, you'll see the pH. The pH is fine, or the F. So substitute the F for the pH. That's fine. So either way is okay. We have magnesium oxide. Okay. Then we have potassium phosphide. Notice all the IDE, phosphide, meaning it's the single element. And then we have calcium nitride. Notice no prefixes. We had nothing said about tricalcium dinitride, just straightforward calcium nitride. Then we have aluminum chloride. Then we have zinc. Whoa. Zinc, Z-I-N-C, chloride. Oh, no, excuse me. What am I saying? Iodide. I was looking at the chloride. And then now we have copper. Okay. Roman numeral 2 oxide. Okay. And then we have lead. Roman numeral 4 uppercase oxide. Okay. And so for all the other metals we did from 1 through 6, because these metals all belong to the sweet 16 group, okay, no Roman numerals. Those are exact oxidation numbers. We already know. We know the oxidation number. All the others have a variable oxidation number, so we have to be specific, okay? We have to be specific. And for example, here we did copper 2, but, copper 1, if you were to use copper 1, then this is copper plus 1 with oxide. Okay, so that means you need 2. So the formula for copper 1 oxide would be Cu2O. The name would be copper, Roman numeral 1 oxide, which is totally different from the one we just did, which is copper, Roman numeral 2 oxide. So right here, okay? So note the difference in Roman numerals. It allows you, that Roman numeral has nothing to do with the Roman numeral on the periodic table, the A, Roman numeral A, 1 through 8A, totally different. Those in the periodic table has to do with the number of valence electrons. These here have to do with the oxidation state of the variable metal that you're working with, okay? Big difference. Don't mix and match the two. They're totally different. All right, so just make sure that when you add them up together, that you have enough of each to make sure that their respective charges equal 0. And like I stated, the most of the time, 99% of the time, that molecule you're working with adds up to 0. However, you can have an example where they don't add to 0. For example, if we were, let me pick one here. if we were looking at the nitrate ion, okay? And the question is, what is the oxidation state of nitrogen when it is bonded to 3 oxygens and has a negative charge? And I'm going to run through this example because in the homework, there are some questions in there that they give you some general equations and they want you to figure out the oxidation number for them. So here, what we do, we set up the problem the same way. Remember, total number of positive oxidation numbers, which is nitrogen. We don't know what that is, but what do we know about the oxides? Oxides, be it in covalent bonded or be it in ionic bond, always have a -2, okay? And there's 3 of them. So what we have here is a total of -6 for the total number of negative oxidation numbers, right? And then the overall molecule is a -1. So I've created here a very simple algebraic equation. Nitrogen -6 is equal to -1, okay? We can solve for nitrogen, add plus on both sides. So now we have nitrogen is equal to +6 minus 1 is equal to +5. So in this type of structure formula, nitrogen has a +5 oxidation number, okay? Unlike when it's nitrogen by itself and it's an ion by itself, it has a -3 oxidation number. The point being that, some of these elements can have a variety of oxidation numbers. It just depends on how they're bonded. All right. But if it's the nonmetals by themselves, 99.9% of the time they have whatever group they're in plus the number of electrons they gain that's their oxidation number. Okay. So this type of formula is very broad for everything. In other words, total number of positive oxidation numbers plus total number of negative oxidation numbers equals the overall charge of the compound. And you can calculate any oxidation number. You're always going to know either the positive oxidation number or the negative oxidation number, and obviously the overall charge. You're always going to know one or the other. Which then allows you to set up an algebraic equation to calculate the unknown. All right, with respect to polyatomic ions, as I stated before, we keep them intact. There are units, and if we need more of them, we need to put a parentheses around it. For example, no different than we just did. They give you OH negative. That in itself, the OH negative tells you I got polyatomic, right? I got an oxygen and a hydrogen, probably more than one atoms, okay? Plus they got a negative charge. So, all right. So same thing, put everything into ionic form. Okay, so the magnesium is a +2. The polyatomic ions given to you has got a -1 charge. That means I need 2 of these, 2 of the hydroxides. Well, needing 2 hydroxides, I use a parentheses as follows. Okay, so the formula is Mg parentheses OH and parentheses subscript 2. It will be incorrect, and I've seen this before, where I've seen MgO, then they put a subscript 2, and I'm looking at that, and I have no idea what that is. That is not magnesium hydroxide. I have no idea what the MgO2, thinking that if I put a 2 there, that gives me 2 hydroxides. So that's not the case, okay? Remember, you keep the polyatomic ions intact, you need more than 1 parentheses. Okay, here we have the potassium and the phosphate, okay? If you go to your periodic table, okay, PO4, you can see right here, here it is, right there. PO4 -3, its name is called phosphate. Okay, so now you got the name. in case you need to name it. And then we have the potassium, which is K, and like sodium is in group 1, then we get the PO4, polyatomic ion. Okay, that means, oh, that's a -3. We need 3 potassiums, ions, okay? And so very straightforward, we just write potassium, subscript 3, PO4. We don't need parentheses around the PO4. And you might ask yourself, how do I know, let's say I'm given K3PO4, how do I know that the PO4 is a polyatomic ion? As a general guideline, okay? This K3PO4 versus K3P, okay? Note here. This is potassium phosphate. Potassium phosphate. This is potassium phosphide, IDE. IDE, a single element. Okay. Normally, if you see potassium by itself, automatically IDE. If right next to it, immediately following, you see oxygen, okay, you're going to see it's going to be either the 8 or the ite, or, you know, this can vary the number of oxygens, but then think polyatomic ion if there's oxygens right immediately following that atom. Okay. Here we have the silver, and no parentheses as stated. We got silver as we part of the sweet 16, so it's got a +1, and we got the sulfate. Sulfate, look at the polyatomic ion table, that is called sulfate. We need 2 silvers for every sulfate. So that becomes silver subscript 2, SO4. Okay. Okay, calcium. Calcium has a +2. Okay, we're given nitrates, 1, -1. Okay, that means we need 2 of the nitrates, meaning that we got to use parentheses because we need 2 nitrates because each nitrate has a -1. So its formula becomes Ca parentheses NO3 and parentheses subscript 2. Okay, here we're if you look this up, this is called carbonate. Look in the polyatomic table, that is carbonate. And obviously, like we talked earlier, copper 2 tells you you are using +2 ion. And then the carbonate, you might be familiar with the term carbonate. You may have seen if you read the label, potassium carbonate, sodium bicarbonate. These are baking soda material. Okay, and so it's both of them are +2, -2, so we can simply put them together as a 1-to-1 relationship, and there you go. And then let me clear this up. Let's make sure we get the naming right. Okay, we have magnesium hydroxide. Okay. How did I get the name? Well, I looked up the polyatomic ion table and it gave me the name. It's hydroxide. Same is true for the PO4. So this is potassium phosphate. Okay. Silver sulfate. Calcium nitrate, not to be confused with nitrite, okay? Because this is the NO3, the nitrite would be the NO2. And then here, this would be copper, Roman numeral 2, carbonate. Now be careful on canvas. When you add the parentheses, first of all, make sure that the Roman numerals are uppercase, okay? Second of all, we've been trying to teach, what do we call it? I've yet to figure out why Canvas occasionally, for whatever reason, students type in the right name and Canvas thinks it's incorrect. I don't quite get it. I mean, I've been following it for a while and I can't figure out tech support's scratching their heads too. So the point being, when you write in the names and if Canvas counts it wrong and you typed it incorrectly, then let me know and definitely will check it out. Sometimes, and we've been teaching it to make sure, because if you add a space after copper, and you can add a space or not add a space. We've been trying to teach Canvas to recognize that. That may be the problem. Maybe we haven't covered all the scenarios yet. So just make sure that if you see it's incorrect, but you know it's correct, shoot me an email, tell me what assignment, what number, and I definitely will go look at it, give you credit. No problems there. Okay, now we've been dealing with these, but keep in mind we can mix and match. Okay. All right, so we had magnesium hydroxide, but you can make that magnesium phosphate or sulfate or magnesium nitrate or magnesium carbonate. Same with potassium hydroxide, potassium sulfate, potassium nitrate, potassium carbonate, silver hydroxide, silver phosphate, silver nitrate, etc., etc. Okay, so you can mix and match the cations and the anions. Just make sure when you put them together that you put them together with the correct number of each, so they balance out to a net zero. Okay. Now, all right. So now we're asked to write ionic compounds given the name. Okay, so we talked about the fixed charge, we talked about the Roman numerals and so forth. Okay, and normally if it's the single anion, we had just simply ID. Okay, so Na is simply sodium chloride, NaCl. Okay, sodium chloride. It would be incorrect to say sodium chlorine, because chlorine indicates that is the diatomic element. Okay, chloride indicates that is the ion of chlorine. Okay. So let's take a look at this. We got potassium, and you might think, oh, bromine. However, it's hooked up, is bonded to potassium. So this would be called potassium bromide. Because I've been giving you a name because you can be going in either direction as far as some of the questions. You can be given the name and they want you to figure out the formula, or vice versa. Okay. All right, next one. We have Mg, which is magnesium, bonded to oxygen, which is ionic in the ionic form. So oxygen becomes oxide. So this is called magnesium oxide. Okay. Note, no Roman numerals. Why? They're part of the 16, right? So it would not be potassium Roman numeral 1. That would be incorrect. Or magnesium Roman numeral 2. That also would be correct. Calcium bonded to fluorine. Okay. And you might think, oh, wait a minute, I got calcium here. And you might be thinking, okay, diatomic, all right, because Fe2. Well, the fact that there's calcium written first, followed by F, tells you you're working with an ionic compound and not the element, okay? So that should be calcium fluoride. You will find that in writing the formulas, like you see here, the convention is this: metal first, followed by whatever non-metal. So calcium fluoride, okay? Here we got lithium sulfide. So along the way, you might be checking to say, is that the right ratio? Well, we know that potassium is a +1, We know that the bromide's a -1, so that's right as far as the formula. We know that magnesium is a +2, and the oxide is a -2, so that's good. The calcium is a +2, and the fluorides are a -1, but there's 2 of them, so that follows. Sulfides are a -2, and the lithiums are +1, each one. But we got 2 of them, so far so good. They're being put together in the correct ratio. Okay, so this one's called lithium sulfide. Okay, and then we got silver, which is a +1, and the chloride, which is a -1. So that ratio is correct. The name silver chloride. Okay, so remember that no prefixes for ionic compounds. So this one, number 4, would not be dilithium sulfide. No, it wouldn't just be lithium sulfide. The only place you'll find dilithium would be in Star Trek, I believe. Dilithium crystals. Anyway, little sidetrack there. All right, no prefixes. Now, when it comes to the polyatomic ions, again, as I stated, they have their own specific names, and that's what you use. For example, NaNO3. Okay. Now you might think, well, wait a minute, how do I know I got a polyatomic ion? All right, well, you see sodium, obviously, so that means that you have an ionic compound. Then you see nitrogen after that, and you might be thinking nitride, right? Nitride, however, bonded immediately right after nitrogen, you have oxygen. So that right there should trigger and tell you, I got a polyatomic ion. Let me go to the table, okay, to look up NO3. And when you do that, you'll find it to be called nitrate. And you'll find it that it has a -1 charge, and the sodium has a +1 oxidation number. So that ratio is correct. Okay. All right. Same scenario here. I got potassium here, and then I'm thinking, all right, I got phosphorus, which is not going to be phosphorus because I got potassium. So I might think phosphide, but then immediately following that, I got oxygen. So bam, I go through the table, look for PO4, and you will find it to be phosphate with a -3 charge, which is consistent with a subscript 3 of potassium. Okay, because potassium has a +1, the phosphate has a -3, so we need 3 potassium ions. Okay, another indication that you have a polyatomic ion is the parentheses. Automatically, parentheses, think polyatomic ions. OH, go to the table, you find it to be hydroxide. Okay, calcium hydroxide. Again, no prefixes, is not calcium dihydroxide, it's simply calcium hydroxide. It's not tripotassium phosphate, is simply potassium phosphate. You will find these prefixes in a lot of labels. I don't know why they do that. Maybe it's a marketing thing or something. I don't quite understand when I start reading labels and what's in your food. A lot of material like this is in there, and a lot of sulfates, by the way, but they use prefixes, which is not correct. And then, and I say correct because there is an organization called IUPAC. It's an international organization. What they do is they have standardized the naming of compounds so that everybody is on the same page with respect to naming compound, be it you're a scientist here or the other side of the world. Okay, and really, it really is. If you think about chemistry, it can be another language, because I recall when I was in graduate school, there was a scientist from Japan visiting our lab, one from Lebanon, and then we had another scientist from Korea. Now, our conversation, our English, it was more, we can communicate, but their English was not the best. My Korean was to zero, and my Japanese was even worse. So, but we were writing chemical reactions on the board, and just we came up with, we were trying to synthesize a compound. It was a team effort, and we were able to communicate just by writing things on the board with the chemical names and the formulas, and we communicated pretty well. Yeah. Anyway, here we go, zinc, and we got sulfate. This is called zinc sulfate. All right. And now with respect to the multiple charge atoms, a variable charge, we got to use a Roman numeral. So question is, well, I know what it is. Okay. I look at this formula and I see, all right, I got CuCl2. All right. I know I got copper. And copper is not part of the sweet 16, so that tells me I got a parenthesis. I got to use a parenthesis, and then I know that I got too many marks here. I think my pen's acting up. Okay, so I can quickly write the parent, the base name. Okay, and so I got copper chloride. No question about it. That is the base name based on the two elements. What I don't know at this time is what's in the parentheses. Which copper am I using? But what do know? I do know that the chlorides, first of all, I do know that the host charge is 0. This is a neutral species here. Otherwise, they wouldn't charge up in the superscript. So it's neutral. Okay. I don't know the charge of copper. So that's not an A, that's a Cu for copper. And I know that the chlorides, all of them are a -1, and there's 2 of them, right? So I got a total of -3. So my little algebraic equation is Cu minus 2 equals 0. So in this case, solve for Cu is equal to +2, okay? So I must be using +2 here. I have to be, since I got 2 negatives in the chloride. So that means that the name would be copper Roman numeral 2 chloride. Okay. Copper Roman numeral 2 chloride. If it were CuCl, okay, then that would be had the same base name, copper chloride, but since I got a -1 for one chloride, that implies that copper must be a +1. So in this case, this will be copper Roman numeral 1 chloride, and this one would be copper Roman numeral 2 chloride. 2 complete different species. Okay, and that's what I mean by for the variable charge metals. You're always going to know what the anion is, okay? And the vice versa too. Sometimes you don't know what the cation is, but you know what the anion, but you know what the cation oxidation number is. Okay, so that means that this is copper 2 chloride, okay? All right, let's take a look at this one, all right? So we know base name, Pb is lead. Lead's not part of the sweet 16, so I know I got to use parentheses. And then oxygen is oxide. Okay, so that's 50% of the name right there. Lead oxide. To complete it, we need to know which specific lead we're working with. So what do we know? We know that the oxygen, the oxides, each are -2. There's 2 of them. That means the total negative is -4. Okay, so it is Pb minus 4, which tells you that lead must be a +4 charge. Okay, does that make sense? So the name is lead Roman numeral 4 oxide. Okay, nickel. Okay, what do I know? Base name, I can write that down real quick. Oh, my pen just died on me. Okay, so I got -3 over here, and the nickel must be a +3. Okay. Clear all this mess up. Nickel 3 bromide. Okay. Now, this is manganese. It is not magnesium. Okay, magnesium and magnesium. Magnesium's Mg, Mn is manganese. But I do know that the sulfates are a -2. Okay, it's one of the polyatomic ions. That implies that the manganese has to be a +2 charge. Okay, so therefore the name would be manganese, Roman numeral 2 sulfate. Okay, here we got copper and then the polyatomic ion. Okay, that is the NO3 is a nitrate, which has a -1 charge. That implies that copper here must be a +1 charge. Okay, so that means that we have copper, Roman numeral 1 nitrate. Just give me this one. Whoop. And then here's interesting one. Okay. Note the difference here. The number 4, we had nitrogen, but immediately following the nitrogen was oxygen. So that tells you I got a polyatomic ion, specifically in nitrate. Here, I just got nitrogen all by itself. So what is that? That is nitride. Okay. CO is cobalt. Okay. And obviously a parenthesis here. We don't know what it is, so we need to calculate it. We know that nitrides have a -3. That implies that the cobalt here must be a +3. So cobalts are very nice colored metals, very beautiful colors. Anyway, this species is named cobalt Roman numeral 3 nitride. Okay, here's one that's a little bit challenging, but we'll figure it out. Okay. We're going to generate our algebraic equation first. So we got a parentheses, okay, so that flags you to polyatomic ion. So you go look it up and you see that that is the carbonate. So you have, it's iron for the Fe, and then looking up the CO3, that is carbonate. It's carbonate. And iron is not part of 16, so we need a parenthesis. Okay, so we need to calculate to determine what oxidation state this iron is. So this is one way. The cobalt, the carbonate is a -2. And there are 3 of them. So that means I got a total of -6 oxidation numbers for the anion, right? There are 2 irons, so I can go 2Fe -6 equals 0. Right? The whole thing equals 0. Again, the -6 comes from the 3 carbonates, which are each -3. The 2 comes from the subscript of iron, telling me there's 2 irons. So now I have an algebraic equation. I can solve for iron. So 2Fe equals a +6, divide by 2 all the way through. So iron is equal to a +3. So this iron here must be a +3. So the name is iron, Roman numeral 3 carbonate. But remember, at a glance, the subscript of the anion is the charge of the oxidation number of the cation. So the subscript of the carbonate, which is 3, happens to be a +3 for the metal. So you can very quickly determine that just by glancing at the formula. Otherwise, you don't see it, run it through like we just said, set up your little algebraic equation and then solve for the metal. In this case, the metal that you don't know. It could be the non-metal at times, or the anion, I should say. All right, so there we go, carbon. Now, as before, you can mix and match. We got lead bromide going on here if you want, lead sulfate, lead nitrate. Guess what? Lead nitride and lead carbonate. Do the same with nickel, nickel oxide, nickel sulfate, nickel nitrate, nickel nitride, nickel carbonate. Same with copper, etc., etc. So now you see how you're building up a little database. And don't forget that you have the study mate on campus. I mean, on the Canvas course. The study mate is, I uploaded 100 plus different formulas and names. So you can use that as flip cards to help you out. And it's basically created like this. We have the cation, the anion, we just mix them all up back and forth. So you have a large number of compounds you have in your database. All right, well, let's do this one here. Got a list of species here, and they're asking you to either give the name and formula. Okay, so we can do both. So number one, you got SR. Well, we got to figure out what SR is. And SR is element number 38, which is strontium. Okay, strontium is a plus group 2 metal, 2A metal, which tells you that it will have a +2 oxidation number when it becomes ionic. Okay, this is the hydroxide. Okay, so that means we're going to need 2 hydroxides. So the formula will be SR parentheses OH and parentheses 2. Okay. All right, here they just want the name. So the general name here is gold. And then chloride. I shouldn't say general name, the base name. Okay, we don't know what the parentheses is, so we got to calculate it. We know that the chlorides each have a -1. There's 3 of them, so we have a total of -3. Okay, and that implies that the gold must be a +3, so that whole thing equals to 0. So that means that is gold Roman numeral 3 in parentheses chloride. Okay. The zinc is a +2, it's one of the 16. The oxygen is oxide, which is a -2. So we can just put them together simply as a 1-to-1 ratio, ZNO. Okay. Here we have a phosphate, and then we got the barium here. Okay, with a +2. Barium is a group 2 metal. It will have a +2 charge. All right, and so we got to combine these two dissimilar charges. So we find a common value, which is 6, like the previous example. That means that we need 3 positive 2s, that's a total of +6, and 2 negative 3s. Okay, so our formula becomes barium subscript 3 parentheses PO4 subscript 2. Okay, barium phosphate. Okay, you might be tempted to call this sulfate, but if you look at the polyatomic ion table, you find it to be sulfite. Okay, so we got lithium with a +1, it's in group 1. We're going to need 2 of them. So we got lithium subscript 2 sulfite. Okay, aluminum has a -2, and excuse me, aluminum has a +3, and the sulfite has a -3. So we got a +3 and a -3. So we can very quickly write the formula as Al2S3, because our common number again is 6. So I need 2 aluminums, 3 sulfides. Okay. And here they want you to just name this compound. So this is copper. Okay, something in parentheses. The NO3 in parentheses is the nitrate. So its parent name is copper nitrate. We know that each nitrate is a -1, so there's a total -2. That implies that this copper must be a +2. So it'd be Roman numeral 2. Copper, Roman numeral 2, nitrate. Copper, Roman numeral 2, nitrate, and we got aluminum sulfide, lithium sulfite for number 5, barium phosphate for number 4, zinc oxide for number 3, gold, Roman numeral 3, chloride, strontium hydroxide for the first one. Okay, and as always, mix and match. You got strontium chloride, strontium oxide, strontium phosphate. Yeah, right here is strontium chloride, strontium oxide, strontium phosphate, strontium sulfite, strontium sulfide, strontium nitrate, and you do the same with zinc and barium and lithium and aluminum and copper. Okay, so now you're really starting to build up a large database of compounds. All right. I think I was going to take totally forgot about taking a break, but let us finish this chapter. We got 15 minutes left, only a few more slides, and we'll knock it out and just call it a day. You know, we'll be ahead a little bit. Okay, here they're asking you to give the formula. So, and whenever you're given the formula, the first thing you got to do is convert them to ions. Okay, and so you got sodium, which is Na plus, right? The nitrite, okay, nitrite sends you to the polyatomic ion table. Yep. And that's that species, okay? All right, so I can combine them together 1 to 1. So the formula is NaNO2, sodium nitrite, okay? Nickel 3, so we're working with nickel plus 3, and then oxide. And so we got oxide, which is O2. So now we have the similar atoms. So we can simply, we need 2 of the +3 and 3 of the -2. So we got Ni2O3, and that would be nickel 3 oxide. Okay. Magnesium converted to ion, so that's group 2, gives you a +2 charge. Iodide is, all of them are a -1. It's a group 7 element, the halogen. All right, that means we need 2 iodides. So its formula is Mgi subscript 2. Okay. All right, cyanide, that is a polyatomic ion, which is a Cn -1. And we also did that in Lewis-Dot structures. Aluminum is a group 3 metal. Okay, one of the 16 that always has +3 oxidation state. So that means we're going to need 3 cyanides. So its formula will be Al parentheses CN3. Okay, that would be its formula for aluminum cyanide. Let me clear that and we'll show you the better looking picture than my hand drawing. All right. So the points here is to, when you're given the name, break them up into the respective ions to determine how many of each you need to put together, and then put them together with the right ratio, okay? And be able to go in both directions. You know, here we're going from name to formula, but be able to go from the formula to the name, okay, back and forth. And also here, you can do mix and match. You got sodium oxide, sodium iodide, sodium cyanide, nickel nitrate, nickel iodide, nickel cyanide, etc. So more for your database. Okay. Now, when it comes to covalent molecular compounds, all right, this is again nothing but nonmetals. Okay, this is what we're gonna talk about now. All right. Okay. First of all, we're not working with ions. So there's no charges. We're still working with oxidation numbers. Okay. And there are partial charges, but in this case, we do use prefixes, specifically these. One is mono, two is di, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8. Occasionally, not always, it's nona for 9, and deca for 10. Okay, for prefixes. So the general format is this. The green here, you got the prefix, if it's there, plus the nonmetal name, followed by the prefix and then the second nonmetal name, but we add the "ide." Recall that the nonmetal, the ones with a negative oxidation number, like oxygen, you know, we use carbon dioxide versus sodium oxide. Okay, in both cases, we use the term oxide. The difference is that for covalent compounds, we use the prefix of dioxide, okay? But the oxide part for the oxygen remains the same. And so normally you're going to have a nonmetal central atom followed by a nonmetal attached to the central atom, and that what is attached to the central atom, that name changes to phosphide, okay? And we'll give you some examples of that here in a bit. Remember drawing? Okay. If it's, we don't use mono for the first non-metal, so only for the second. So you got carbon dioxide, then you put carbon monoxide. Okay, it's not monocarbon, it's just simply carbon. So here we got carbon dioxide, okay? And then let's do this one. This one would be carbon monoxide. Okay, remember we got prefixes, that's how we distinguish between the two. Two totally different covalent compounds. Okay, dioxide and monoxide. Now, here, phosphorus is the central atom normally written first, so it would not be phosphide. If it was written second, then it would be phosphide, but here is written first. So we write the base name like we were doing earlier with respect to the names of the required Roman numerals. So we go phosphorus, and then oxide. Okay, not oxygen, but oxide. Okay, so that's the base name. Now we go back and add the prefixes. There are 2 phosphorus, so it's diphosphorus, and there are 5 oxides, so it's pentoxide. Now, from an English perspective, my English teacher will have a fit. You'll see in here, when you got the penta prefix ends with a vowel, and you're going to attach it to another vowel, you're supposed to drop the A, so it'll be pentoxide. Is technically the correct name. If you forget to do that, I'm not going to mark you off because you forget you drop the A. So if you write pentoxide, that's fine. Pentaoxide, that's fine. Okay. My English teacher will turn in her grave right now, but okay. All right. So we got diphosphorus pentoxide. All right. Here we have again phosphorus in the middle. Okay. So again, my recommendation is first just look at two elements that are involved. Notice that the fluorine is after the central atom, so it's still phosphorus to begin with. And fluoride. And come back and use the prefixes. You don't need a mono for the first one, but you need trifluoride for the second one. So that name would be phosphorus trifluoride. Here we have iodine and fluoride. So we got iodine, and then fluoride is the best name, and then come back and add the prefixes. There's 7 fluoride, so that becomes heptafluoride. So it's iodine heptafluoride. Okay. Notice we didn't change the name of iodine. Iodine is the central atom. Okay. And so we keep the name iodine. In fact, if you think about it, the oxidation number for iodine in this state is a +7. Normally we think of it as being a -1 when it's an ion. Okay, so given the formula, write the name and vice versa. So we have here Br3O8. All right, so given the formula, we're going to write the name. So you write the base name first. We got bromine. Notice it's not bromide. It's written first, so it is a bromine. Okay. And then an oxide to denote the base name. So it's bromine. So we go tribromine, oxide. Okay, because there's 8 of them. Okay. Notice the difference. If this was, let's say, iodine, and for argument's sake, let's put 5. Well, this would be iodine, bromide, pentabromide. Notice the difference? Here, bromide is after the central atom, so it becomes bromide. In this example, bromine is one of the central atoms, is written first, so it maintains that bromine. Okay? There's tribromine octooxide, which should be without the A. All right, now we got the central, we got phosphorus. And then sulfide. Because it's IDE, because it's after the central atom. Okay. Unlike this one, where it'd be called sulfur dioxide. Sulfur because it's the first. Sulfide because it comes after. So then we add the prefixes tetraphosphorus, and 7 would be hepta sulfide. Okay. Tetraphosphorus heptasulfide. Then here's this one, sulfur, it's first, and then 3 oxides, so trioxide, sulfur trioxide. Okay. Sulfur because it's first, sulfide because it comes after. Okay, it's bonded to whatever the central atom is. In this case, in central atoms. All right, then finally, iodine hexachloride. So we got the name, and working opposite. Before we're naming it, we write the base name. Here we write the base formula. We have iodine and we have fluoride, right? Now we just come in to look at the prefixes, hexa, so it's 6 fluoride. Okay. And then trichlorine, notice trichlorine, meaning it's the central atoms here, followed by the oxygen. It's not chloride. If it was chloride, it would have been after. So I can't overemphasize that aspect, how we distinguish the two. So chlorine, there's 2 chlorines, pentoxide, meaning 5 oxygens, okay? Okay. As compared to, let's say, iodine, we could make that chloride, iodine hexachloride, okay? In that scenario, because the chloride comes after the central atom. Now, these that have more than one, I'm calling it the central atom, like the first example, but there's really 3, it's a complex. There's 3 bromines and there's 4 phosphorus. We're not going to go into the structure, but that is the formula for the species. All right, next one. Let me hurry up here because we're getting close to the end, and I think a couple more pages will be done. So we got diphosphorus tetride. It's a tongue twister. Tetriiodide. Okay, if you take that A out of there. All right, reminders that prefixes are only for the covalent compounds, okay? And Roman numerals are only for those metals that have a variable oxidation number. They're not for the 16, the good old sweet 16. I call it sweet 16 because it helps you remember, hopefully, those 16 metals, no Roman numerals, okay? And let's see what else. Polyatomic ions, we don't change their name. They are what they are. They've been assigned a name. They're in that table. Okay. And then you might want to try these at home, but you should come up with barium chloride, nitrogen dioxide, iron 2 phosphate, okay, diiodine tetroxide, and then we got silver sulfate, and nickel 3 sulfide. Also, keep in mind, we can do mix and matching here for most of these, especially the ionic compounds. So build up your database. So do your worksheet. There's, don't forget the nomenclature. Only 2 people have really attempted the nomenclature. We got done with this chapter. We're gonna, next Friday, I'm gonna talk about some additional nomenclature information and jump into the next following chapter. But do start working on taking that nomenclature exam so you can get a feel for where you're at. So remember, you gotta get at least 80%. Anything less than 80%, Canvas converts it back to 0. But I do go in there and I check your answers, and I do give you credit for answers that maybe Canvas may inadvertently not give you credit for. So, and you have an unlimited number, okay? I will be converting those grades to 0 that people have not attempted. So that, and I'll explain in the email, people get all upset because I put a 0 in there, even though it's not due until the last day. But I do that on purpose so you can actually see your true grade, because that assignment is not really incorporated into your grade until it's graded. And if you wait until the last day of class and you can't make that 80%, 10% can either knock you off a grade scale, or it can even push you up a grade scale if you're on the border. Okay, so anyway, thank you for showing up. I appreciate it. Let me see, we got down with chapter 3. Okay, You guys, any questions?
Yeah, Dr. Fred, can you hear me?
Yeah, I can hear you.
Okay, good.
You're kind of far away, but I can hear you. Go ahead.
Okay, well,
I just wanted to ask, and maybe you said this, but on that nomenclature test, if we take it and we get an 80, but maybe we want to take it again and try for a higher grade, how do we
Yes.
let you know that?
You just keep going in there and repeating it. You have unlimited attempts, even though you're at the 80, you're not happy with that. You just go back in, start it again.
Okay, good.
And
I
then-
just didn't know if once we reached 80, it would just submit
No.
and we'd be done. Okay,
No.
good. All right.
I've had people go back and continue through the end of the semester till they get that number they want. But but that 80 is just what the departmental has stated that one must maintain to get that. Yeah. So, you know, you just keep trying, keep going. I will go check it every time there's a new score or something like that.
Okay, because I
Well-
haven't tried it because I figured there was no way until we got through chapter 8 that I would even know enough to make an attempt. But
Okay.
once I digest all of this, I'll probably start making
Oh,
some
yeah.
efforts.
Yeah, in fact, and don't forget the study mate. Let me go up to. Okay, let me share this.
All right.
Okay, on the course website,
Mhm.
on the far left. Now yours is going to look a little bit different than mine. Let me see if I can go into the.
Yeah, I think I looked at that study mate.
Yeah, here we go. Right here, study mate. So if you click on that, okay, then just continue. Don't show this again. I don't need to know that. But there's one here called Nomenclature Practice.
All
okay?
right.
You click that. Now, I would recommend, there's a variety of, everything I uploaded, you can put into about 4 or 5 different ways of presenting it. You can make a crossword puzzle. I would recommend only the flashcards and matching because StudyMate doesn't quite understand subscript and parentheses, and it makes it a big mess if you go crossword puzzle. But if you do flashcard, you come up to this, and there are 143 compounds that I uploaded. So if you notice, his name here, dioxygen difluoride.
Right.
Okay. Now, given what we just talked about, what do you think the formula would be? Well,
Well, let me just die.
you see, it'd be oxygen and fluoride, right?
Right.
The base name. Di would be 2 oxygens, and difluoride would be 2 fluorides, right?
Right.
Would you agree with that?
Well,
Okay.
di is
Yeah.
2.
Yeah.
Yeah.
Okay, so let's double check. There's your formula.
Excellent.
Okay,
That
now-
I will definitely use this.
Okay, and then keep in mind that it doesn't support subscript. So that 2 after the O is a subscript. Okay.
Okay,
And
that
then
makes sense.
you go to the next one. And what I did, I try to maintain as many examples as possible from the nomenclature
Mhm.
exam in here. So here we have sulfur, where'd it go? We have sulfur dichloride, so we go sulfur and the chloride as a
With the
base
2.
name, and then we got a 2 here. So that seems to be the formula. Let's find out. There it is. Okay.
Well, I think getting through chapter 8 will help a lot of us finally jump in because I would not have known that before today. So
Okay. Okay.
yeah, that'll help a lot.
Yeah, some people had jumped on it. They're like, why don't we give it a try? And that's fine. If you haven't touched it, that's okay too. You know,
Right. I mean, some
not
of
a
us
problem.
never had it in high school, never had chemistry in high school. And I bet you that those that have already attempted it must have, you know, had some early in chemistry.
Yeah, and if you do, I forgot, I think we're not there yet, but if you make that 80% before, I have it written down, I think it's the 11th week. you get a 2% bonus.
Oh.
on this. Yeah.
I thought
so-
that already passed. I thought that was a date in September.
So is this September?
I think so.
Okay, it might be
Really-
so. I got.
It was
I got-
really early. Yeah.
Yeah, I got my days all mixed up here.
But if you want to
Anyway.
extend it, I don't think any of us will argue.
Oh, well, I might consider that. Give it some thought. Yeah, maybe give you to the end of today. No. Maybe.
No, I have a lab test. We have our
Oh.
lab test today.
Oh, yeah. Okay, maybe I'll consider that option. Let's see.
All right.
Maybe for the next 2 weeks or something,
That'd be
Maybe
good.
something
Yeah.
like that. Okay,
All right.
I might do that. All right, it's good,
All
good,
right.
good suggestion. That'd be a good incentive.
Yeah, it would be because if what's covered on that is what we've just covered in chapter 8, then
Mhm. Yeah.
everybody should be trying
pretty-
it.
Yeah, at least
Right.
give it a shot. Now, I'm gonna continue with another part of this chapter. If you look at the module of, the module with respect to nomenclature, there's
Right.
other files in there. And another PowerPoint slide that I'm gonna talk about next Friday.
Okay,
It's an addendum to this nomenclature. And
all right.
that would help out with like these polyoxy ions, like the sulfate and the sulfite, because the nomenclature uses quite a bit of those.
Okay. Yeah, I noticed there were a lot of printouts for 8. I've got all of those. I always print everything that,
All right. Yeah,
I can
yeah.
refer back to. So,
Okay, that's good.
well, good. Thank you
Yeah.
very much. I
You're
appreciate
welcome.
your teaching and
All right, well,
I'm enjoying
you.
this.
okay.
Yeah.
Thank you very much.
All right.
All right, well, you guys have a good week and we'll see you next week.
See you next Friday. Have a good weekend.
All right, you
care.
too. You take care. Bye-bye.
Bye.
Trey, you had a question? Say, Trey?